Hi, welcome back to Math 533 Topics in Euclidean Geometry, and welcome to week 13 of the semester. We're almost done here with our semester, and we are now finally at the most famous theorem of geometry, arguably the most famous theorem in all of mathematics, the famous and the beloved Pythagorean theorem. So we're going to see two proofs of this theorem this week. We're also going to see something called the converse to the Pythagorean theorem, which is the one that is often used in practice. So we will see that, and we will also introduce the notion of area and use that to give us a second proof of the Pythagorean theorem. Now let me point out something very important, and that is that the Pythagorean theorem is a theorem of Euclidean geometry. It is not a theorem of hyperbolic geometry. It's only true in Euclidean geometry, and at some fundamental level, it is telling you about the homogeneity of Euclidean geometry and the fact that triangles at all scales look the same, which is what we've been thinking about when we talk about similar triangles. So the Pythagorean theorem tells you a lot about similar triangles, and similar triangles tell you a lot about the Pythagorean theorem. Okay, let's go ahead and state it and look at a first proof of the Pythagorean theorem. This first proof is going to have a very algebraic kind of flavor to it. Let's state it first. Suppose triangle ABC is a right triangle and it has its right angle in the vertex C. Then the sum of the squares of the two sides adjacent to the right angle, also called legs of the triangle. So in this case, it's AC squared plus BC squared. The sum of those squares is equal to the length of the hypotenuse squared. So that's the distance here, AB squared. Okay, conventionally what we do is we write a lowercase letter for the side opposite a given vertex. So here I have little c is my hypotenuse because it's opposite big C. And I have, so here's my little c. I have little a opposite big A and little b opposite big B. And if I write it that way, I get the famous a squared plus b squared equals c squared. So let's prove this theorem. And for the proof, we need a lemma. So the first lemma that we need is that if I have a triangle ABC and I have an acute angle in, so let's say here I have this acute angle in A, then the foot of the altitude dropped from C is on the ray AB. So in my example here, I have a very nice acute angle in A, and I happen to have an obtuse angle in B. So it's illustrating exactly what we need to worry about. However, if both the angle in A and the angle in B are both acute, then obviously F has to be on the segment AB, because it's simultaneously on the ray AB and on the ray BA. Right, so this one, it's a little exercise for you to do. I'll give you the hint. If you suppose that F is on the opposite side of A, so over here on the left, then you can grind through with the angles, and you can show that you must have that the angle in A is obtuse. Right, so you can basically prove the contrapositive of this statement. Okay, so now we're ready for a first proof that we're going to see of the Pythagorean theorem. And this one is kind of algebraic in flavor. So what we do is we drop the altitude from C, and we label that foot F. F for foot, right? So that's, I've dropped this altitude here from C, and I have my foot F. Now, by the lemma, F is between A and B. And that's important. So if I name the distance from A to F, I name it x, and the distance from F to B, I name it y, and I name h to be the height here, so that's the length of the segment CF, then the first thing we see is that x plus y together is the length of the hypotenuse, so is that quantity c. Right? So for that, this equality here is the content of our lemma that we that we didn't prove, but that I left for you as an exercise. Okay, now here's the tricky argument. If I look at triangle ACF, what I'm claiming is that this triangle ACF is similar to my big right triangle, right? It's a small right triangle here because it has a right angle in F. And the argument comes from looking at the angles, right? So the angle in A is obviously congruent to itself just because it's equal. The angle in F is congruent to the angle in C in my big triangle, right? Because they're both right angles. And then by the angle sum, the third angle then has to be the same, right? Because angle in A, angle in F, some unknown quantity add up to 180. I have angle in A, angle in C, and then the angle in B add up to 180. So that means that this angle in B here is congruent to this angle in C there in my little triangle. So now I have that the three angles in ACF are equal to the three angles in ABC, and therefore by the angle similarity theorem, we get that these, right, this triangle here on the left of my altitude, that triangle is congruent to my big triangle. Okay, we're going to play the same game on the one here to the right of my altitude. So that's this triangle here, CBF. And CBF, by the same argument, is going to be similar to the big triangle ABC. Okay, so now we can apply the side-side-side similarity theorem to say that the ratios are the same. So here I'm saying the ratio of B over X is the same as the ratio of this whole side C over B. Right? I'm looking, this is the ratio of the hypotenuse in ACF divided by the length of the side adjacent to the angle A. And then C over B is the hypotenuse of ABC, and I am dividing by the leg that is adjacent to that same angle A. Right, so that's this first equality on the left here is coming from looking at the big triangle and my little triangle ACF. We do the same deal with the triangle on the right, right? And that gives us then, right, so that's the hypotenuse of the little triangle divided by the length of the leg adjacent to B, and that's going to be equal to the hypotenuse of my big triangle ABC divided by the length of the leg adjacent to B. Okay. So now we just do a little bit of algebra. I'm going to cross multiply my two statements involving ratios, right? So that first one gives me b squared equals cx. The second one gives me a squared equals cy. And then I'm reminding us from before that c is equal to x plus y. So now if I take a squared plus b squared, I get cx plus cy. I factored the c, so I get c times x plus y. And then I sub back in what x plus y is, and that gives me c squared. And that completes the proof of the Pythagorean theorem using this algebraic argument and similar triangles.